Today we're going to talk about 7-2 ratios in similar polygons. So what does similar mean? Similar means the same shape, but not necessarily the same size. A great example of this that you've definitely seen is a model toy car. It's the exact same car, just obviously not the same size as the actual car. So checking out similarity in triangles, here I've drawn triangle 1, 2, and 3. Now what I did was I drew triangle 1, and then I just made triangle 1 exactly bigger. I just enlarged it, and that's triangle 2. And then we have triangle 3 off to the right. Now, what we can see is that 1 and 2 are the same shape, but they're not the same size. So what we call them is they're similar. How we write that is we say triangle 1 is similar to triangle 2. Now this is a new logo, or a new symbol for us. This here means similar. It looks very, it's very close to what our congruent sign means, but it is similar. Notice it doesn't have the equal sign underneath. Now let's compare triangle 1 and triangle 3. Now, triangle 1 and triangle 3, triangle 3 is a right triangle. Triangle 1 is not a right triangle, so they're not similar. It's not the exact same shape. So we say triangle 1 is not similar to triangle 3. I drew the similar sign and put a line through it. So now that we know what similar means, when exactly are polygons similar? Well, two things need to happen. Their corresponding angles have to be congruent, so meaning that they have the same angle measurements, and the corresponding side lengths must be proportional. So just a quick example applying this fact. Is triangle ABC similar to triangle JGH? So we have our two triangles drawn, and just like how we name congruent triangles, or shapes for that matter, starts with letters that correspond. So the A and the J are corresponding, the B and the G are corresponding, and the C and the H is corresponding. So to determine if it's similar, are the angles congruent? So A needs to be congruent to J, is it? Well, here we have A and we have J over here. We don't necessarily know, so let's move on. Let's talk about angle B congruent to, it should be congruent to angle, let's see, B is the second, G is the second. So it should be congruent to angle G. Is this true? Yes, it is. That's given to us. Now we also need angle C is congruent to angle H. We look here, angle C is 59, H is 59, so we do have congruence there. And lastly, as we talked about before, angle A must be congruent to angle J. Now I skipped it because we didn't necessarily know, but now we do. By the third angles theorem, which says that if two angles are congruent in two triangles, then the third angles will also be congruent, which makes sense. So yes, we have all triangles congruent, or rather all corresponding angles are congruent. Now we need the corresponding side lengths to be proportional. So what exactly does that mean? Well, the corresponding side lengths would be, let's see, the first and the second, which is AB, and the first and the second, which is JG. So we're talking about proportions, so we're going to talk about division here. So AB over JG. In this case, we have AB is 10, JG is 5. So these two have a ratio of 2. Now continuing here, we also see, let's talk about the first and the third, which is AC. So we have AC over the first and the third, which is JH. AC appears to be 11.6, and JH is 5.8. 11.6 divided by 5.8 is 2. Okay. And let's move on to the second and the third, So BC over GH. What do we get here? We get BC 6 over 3, which gives us 2. Now because all of these numbers match up, because we have 2's all right here, this second criteria is matched, or is met, because all these side lengths are proportional. We have a a ratio of 2, 2, and 2. So yes, these polygons are similar. Now we come to a term called the similarity ratio. The similarity ratio is a ratio of lengths of the corresponding sides of two similar polygons. And now I made the comment, in the last example, the similarity ratio of triangle ABC to triangle JGH was 2. That was where all those ratios met up and they were the number 2. That there was what we called the similarity ratio. So using an example here, what is the similarity ratio of two questions? Part A is the similarity ratio of triangle ABC and triangle DEF. The second question is triangle DEF and ABC. They both look very similar. We're talking about ABC and DEF in both of them. But notice the order. This first problem we have ABC first. The second problem we have DEF first. There is a difference. So let's go ahead and do part A. Part A is what's the similarity ratio of ABC and DEF? So what we're looking for is that ratio, but we're on the top of this ratio, or of this fraction, we're going to put the side lengths from ABC. So let's see, let's just first do the first and the second, which is the length of AB, which is 20. So let's put 20 over, should match up with DE, which is 15. So it's 20 over 15, which reduces to, let's see, you can divide both by 5. That turns into 4 over 3. We can continue. We will notice that it's going to be a 4 over 3, but let's continue to do BC, which is 24, over the second and third, which is EF, which is 18. Both of these divided by 6, so we see it's 4/3 again. And we can finally do the last one, which is going to be 16 over 12. 16 over 12, which gives us divide by 4 again, which is 4/3. So for part A, our similarity ratio is 4/3. Now for part B, the question says triangle DEF and ABC. The difference here is that we start with the lengths from DEF first. So we have, let's see, the first and the second, which is DE, which is 15. It's going to be 15 over the first and the second again, which is, let's see, AB, which is 20. Both divide by 5, so we have 3 over 4. And we can continue this using the exact same method, but what we notice is that our answer for B is 3/4, which is different from our answer from A, which is 4/3. The reasoning is because this order actually matters. It matters if you're comparing ABC to DEF or DEF to ABC. So be very careful with that order. Remember that the first one you're talking about goes on top. The second one goes on bottom. Let's go ahead and use similarity ratios to find the length of the model to the nearest inch. So notice we have an actual car here and the model car. Now, I'm telling you that these two are similar shapes, so it's assumed that these two are similar. And so they're going to have a similarity ratio. They're going to share that similarity ratio, as in the ratio of 6 to 2 is going to be the same as 14.5 to x. It's going to be the same ratio. So let's go ahead and attempt this. What we do know is that, let's talk about, well, we're talking about the model to the car. So let's talk about the car. Let's say that we know the width of the car, and this is because they're going to be similar. So the width of the car over, well, what is the width of the car? What's that? What's the corresponding part to the model? Well, we're talking about the width here, so let's talk about the width here. So this is also going to be equal or over the width of the model. Now, we could instantly just throw in that width of the car and width of the model, but furthermore, what we know is that if the width of the car over the width of the model, whatever that is, because these are similar shapes, we know that it will also be equal to the ratio of the length of the car and the length of the model. Now we're just going to be plugging in and then solving. So what is the width of the car? Well, in this case, we have 6 feet. Notice the differences here. 6 feet, 2 inches. If we do a little conversion here, you can multiply by 12. You see that this is 72 inches. Again, all we did was multiplied by 12, sorry, by 12. So we see it's 6 times 12 is 72. So we have the width of the car is 72 over that 2 inches of the model. Now this should be equal to the length of the car. Again, if you multiply by 12, because we're going to inches now, so multiply by 12 and you get 174 inches. So the length of the car is 174, and we do not know the length of the model, so let's call it x. Now, we know how to solve this now. We know how to solve this ratio here. 72 over 2 is equal to 174 over x. Notice again that we used the width over the width, length over the length, as we should be. Compare the similar shapes, or the similar corresponding sides. So 72 over 2 is 36. So we know that 36 will be equal to 174 over x. Solve for x. We know that x is equal to 174 over 36. This is where I did that cross multiplying thing. I can multiply my x up and my 36 down. And therefore I see, let's see, what is 174 divided by 36? It is 4.833, and that's repeating. So since we're going to the nearest inch, we know our answer should be about 5 inches. And that's it. We've used proportionality ratios or similarity ratios to come up with this. Write down any questions you have, and have a great day.